Hello everyone and welcome to this Amazon Web Services webcast where we will cover big data architectural patterns and best practices on AWS. I'm Jorge Lopez, lead for Big Data Solutions Marketing at AWS. And before we begin, I would like to walk you through a few items. On your screen, you can see a Q&A pod. You can use this pod to submit all your questions for our presenters at any time. Today's webcast is being recorded, so we will send you a follow-up email with the URL to the recording, as well as a link to the presentation deck within the next few days. And again, welcome to today's webinar. Our presenter is Siva Raghupati, Principal Solutions Architect at AWS. As the lead for the America's Big Data Solutions Architecture team, at AWS, Siva guides developers and architects to build successful big data applications on AWS. Previously, as a principal technical program manager for AWS Database Service, he gathered emerging NoSQL requirements and wrote the first version of DynamoDB product specification. In addition, we have a couple of AWS big data experts, Keith Stewart, EMR Solutions Architect, and Babu Elumalai, Solutions Architect. Keith and Babu will engage with you and answer your questions throughout the presentation, so please feel free to submit your questions anytime. We'll also try to allocate some time at the end to address some of the additional questions. And now let's go to the fun stuff. So let me turn this over to Siva.
Hello and welcome. So I'm delighted to be here, and I'm going to today try to share my experiences helping customers build big data applications on AWS, as well as experience actually building some of the big data services such as DynamoDB and relational database service, etc. So let's get started. And so in terms of the agenda, I'm going to lay out some of the big data challenges that our customers are having and solving, and how to simplify big data processing. This is a question that we often get asked, and I'm going to give a processing pipeline that would actually simplify big data processing for you. And as I walk through the various stages of big data processing, I'm going to also outline what technology should you use, how, and especially why, because if you answer the question why, everything else sort of falls into place, is how it is played out for me. And towards the end, I will give you a reference architecture for big data on AWS, and also substantiate the reference architecture with a couple of design patterns. And so I have a lot to cover. So I think I'm going to skim over some of the slides, but I felt that slides are important, so I'm going to leave that slides on for later perusal. So let's get started. So the volume, velocity, and variety of big data is ever increasing. As a solutions architect, what I feel on a daily basis is customers are building systems that can deal with millions of requests per second, and I repeat the term, millions of requests per second, billions of events per day, and tens or hundreds of terabytes of data flowing in per day. Again, these systems were hard to build even a few years ago, and interestingly enough now, a handful of developers, in many cases one or two developers, are able to build these kinds of systems in a few days or a few weeks. What kind of design patterns and architectures are successful companies using is something that we'll touch on as part of this talk. The other scenario is more and more companies want to be customer-centric. The competition is intense, and how can you add more value to customers? How can you be more agile? Is the challenge that companies are facing. As a result of this, companies are trying to evolve batch systems to real-time and real-time systems to predictions. What does that mean? For example, instead of actually giving you a bill at the end of the month, won't it be nice to alert you that you're in the process of going to breach your thresholds or your budget or a plan? And again, batch processing is dealing with data that has already happened. Real-time is actually dealing with data or information that's happening now. And predictions is what may come in the future. So wouldn't it be nice to say, you are in the process of, your spend is high enough that you will breach your thresholds. So maybe you should do something about this, either get a new plan or reduce usage, etc. So customers are expecting, predictable systems or predictive systems as well. So how do you build predictions into your big data processing pipeline is something we'll touch as well. So luckily, there's a plethora of tools to help us, solve these big data challenges. On the left side, I call this the zoo of big data technologies, starting with the elephant Hadoop to Pig, Spark, etc. If you go to any big data conference, you probably have noticed that Spark is the answer, no matter what the question is these days. But how does Spark help you solve problems? I think we'll look at that. Also, the other piece is that on the right side, we have AWS services such as Amazon Elastic MapReduce, S3, DynamoDB, Redshift, AWS Lambda, Amazon Machine Learning, etc. So every year we launch a bunch of new services. As an architect, how do you build an architecture that'll factor in the existing tools and technologies as well as open the architecture, for the future, so you can actually plug in a newer component as you move forward. That's something that that customers need to be aware of and build pluggable systems. And so again, the most predominant question is is there a reference architecture for doing or handling all the challenges that I went through? What tools and technology should I use? How and why? Now, before I start to attempt to solve this problem, there's a few architectural principles that I have seen play out in almost all the big data systems I've helped build. I'm going to walk through this at the beginning, and then I'll give you specific examples as I go through. First, if you're dealing with building big data systems, with the tons of data coming in and a lot of data going out, one should build decoupled systems. How that may look like is data going into a store process stage. So you're going to use a storage subsystem to decouple producers and consumers, if you will, so producers can, put data at their own rate, and consumers can consume data at their own rate. How do you use this principle in your big data pipeline? We'll cover that. Also, when we build services at AWS, we build them to do their function extremely well at a low cost. And how do you choose the right service? I think you should be using, the data structure or access patterns, the latency and throughput characteristics of both the service as well as your needs to pick the right tool. I'm going to give you some guidance on how do you think about that problem. The other piece is, if you look at any big data processing pipeline, I think this most frequently happens in ad tech as an industry. For example, many ad tech customers serve millions of requests per second. 1 or 2 or 3 or 4 million requests is common these days. And billions of events per day are terabytes, tens or hundreds of terabytes of data flowing in. When you look under the covers of all these systems, they use a Lambda architecture principle. What does that mean? That really means actually, building a system. You have your batch processing pipeline and a speed processing pipeline. Answering by compositing, the questions or answers from these two pipelines, and building a composite system is fairly important. And then the other piece is that log use your database is a principle that's very true to big data. How do you incorporate these principles into your architecture is something we'll cover as well. Again, I talked about large-scale systems being built in a week or in weeks or days. Leveraging AWS managed services allows you to do that fairly fast. So how do you stitch managed services into your end-to-end big data processing pipeline is something we would look at. Last but not the least, big data should not be equals to big cost. If big data equals big cost, there's something wrong, or it's going to break the bank. So you need to be cost conscious when you build big data systems. And now, applying all these principles, let's try to simplify big data processing. One way of thinking about big data processing is to think of that as a pipeline comprising of data coming in one side and answers going out on the other side. Depending upon what you do, you may go through various stages. The typical stages look like this. It could be either ingest or collect, store, process, analyze, and it may be visualize. That could be your stage. Again, it depends on what you're doing there as well. Typically what happens in a big data processing pipeline is the paradigm of store process repeats itself until you shape the data to how you want the answer to be delivered. And so there's a cyclical process that happens there, and before the answer is sort of delivered. And what governs what you put in between, data coming in, answers going out, is actually governed by what I call as a time to answer, or the pipeline latency, the pipeline throughput, which is a factor of the request per second going in and the payload size, and last but not the least, the cost. As long as you can basically answer the questions within the time to answer, dealing with the right throughput characteristics and the cost characteristics, your big data problem is solved. In essence, that's what we're going to do. That's what happens in sort of every big data processing pipeline, if you will. So now let's look at the ingest state in detail. So when you're dealing with data ingest or collect, typically I look at this as different types of data coming in. For example, transactional data feels like applications like web applications or ad serving applications, do tens or hundreds of thousands of requests per second or millions of requests per second. It feels like it's talking to your subsystem, or your application is talking to a database, lots of database reads and writes. Then most recently, search is very popular. For example, Logstash, data, Yellowstack, sending data using Logstash and going into Elasticsearch and being surfaced via Kibana is another important pattern. And then, file data types. So typically, if you look at any clickstream processing system, typically what happens there is the application servers collect log files, and the log files are actually loaded into a Hadoop cluster for processing. You're dealing with either file data. Typically, the file data goes to a file storage subsystem. Like more recently, with the advent of IoT devices and sensors, etc., streaming data is being more frequently sent to streaming storage systems. So the transactional data goes to what looks like databases. Search data goes to search. File data goes to file storage subsystem, and the streaming storage subsystem. Streaming data goes to streaming storage subsystem. How do you pick the right technology in each one of these pieces? Let's look at the storage in more detail. So we'll go bottom up. Let's deal with streaming data first. This is data coming in from devices and sensors, or IoT gateways, for example. Typically the most common services used there, I'm going to split that into AWS managed services and unmanaged services. Amazon Kinesis, most recently DynamoDB Streams, which exposes both tables and streams. SQS and SNS has been there for a while. SQS is a simple queue service, and SNS is simple notification service for PubSub. Typically these are the four managed services that people think of when they think about sort of streaming data. More predominantly, I would say Kinesis. In the unmanaged space, Apache Kafka is extremely popular. There's a lot of large-scale systems built on top of Apache Kafka, and a lot of these workloads are moving to Kinesis because of the fully managed characteristics of Kinesis. And other factors. We'll look at the differences and contrast them as we go forward. So before we get into the details, I want to lay out a little bit of why stream storage, what type of function stream storage does. The stream storage decouples producers and consumers, and so producers can send data at any rate, and consumers' application can parallelly consume data. And it provides a persistent buffer. So typically what happens is when you're dealing with the low energy device, it doesn't really have the memory or storage to keep the data for a long time. It needs to hand off the data that it's creating to another subsystem where it's persisted in a durable fashion. So the stream storage subsystem, does that function. And, collect multiple streams of data. When you're dealing with devices, there may be millions of devices. And then what happens is the stream storage subsystem gives you a place to write reliably collect data from millions of potential endpoints or sources. And one of the key aspects of a stream storage subsystem, it preserves client ordering. What I mean by that is, for example, if the producer 1, which is the red producer, is sending packets 1, 2, 3, and 4, a consuming application that written to consume the data can actually expect that the data comes in the same order as what the producer sent, provided the producer actually uses the notion of a key and says the key equals red, and then if it puts the data into a Kinesis stream or a Kafka topic or a DynamoDB stream or DynamoDB table, then what happens is that the consuming application can do things like what came 4 came after first. This characteristic is very useful. For example, if you think of the clickstream data, if somebody is browsing through your website, and then won't it be nice to know where did the customer abandon the cart? Where did they get confused? So if the data is captured by a consuming application, which can predict exactly, which can actually analyze the click stream and say where the customers abandoned the cart, maybe that may be an indication of something is not working right in your website. How do you build? So the storage subsystem enable you to do such smart processing. The other piece is this is also called streaming map reduce. The idea that that all the data comprising sent by producer one can be processed by a single thread by a consuming application is called streaming map reduce. This is built into stream processing systems. And parallel consumption, let's say if you're a CEO or CTO, agility or time to market is fairly important. If you have 4 or 5 teams building features of the same clickstream data flowing in, you want them to, all of them to consume the data and run at their own speed rather than being dependent on each other. So from a business perspective as well, the stream storage subsystem enable you to multiple consumers to consume from the same stream and then build features at their own rate, so they're not dependent on each other, and eventually it increases the agility or time to market. So often I get asked the question, what about queues and PubSub? How does that fit into this? I just wanted to touch this briefly. The queues and PubSub, enable you to, they serve as decoupling mechanisms, they serve as a persistent buffer, they have the ability to collect multiple streams, but what they don't have is there's no client ordering being preserved. The example I walked through of where the customer abandoned the cart, it's hard to build with queues and PubSub. There's one exception to this. If you use an SNS and if you actually have multiple queues, actually where you can bifurcate some of this as well. But in general, this is not a good technology to build classic stream processing applications, but you can use them as a persistent buffer or to aggregate data from multiple streams or decouple producers and consumers. And to get more concrete here, which stream storage system should you use? And so what I've done here is actually I picked out the various characteristics such as managed, ordering, delivery, lifetime, replication, going down to cost, etc. So let's compare Kinesis and Kafka, for example. Only the first 3 services, Kinesis, DynamoDB streams are managed services. Kafka is not. In terms of ordering, except for SQS and SNS, all of the other services, Kinesis, DynamoDB streams, or Kafka, is order preserving. Delivery. In terms of delivery, when you have a downstream client actually consuming the stream or a topic, in most cases, it's exactly one's delivery. At the edge conditions, when you're using Kinesis and Kafka, for example, the consuming application may see the same record twice. So, for example, if you're building a billing systems or metering systems, if you know that it's not exactly one semantic, then you can build deduping into it. No customer likes to get double billed for that usage. So if avoiding double billing is important, then you need to build deduping into your system. So that's what I'm trying to illustrate there. So in terms of lifetime of the data staying in the systems, Kinesis allows, for Kinesis, the data stays there for 7 days. This is a new enhancement. It used to be 24 hours before. And for DynamoDB streams, the data you persist in a stream is kept for 24 hours. The data in the table stays there forever. And in the case of SQS and SNS, it's 14 days, and it's configurable in Kafka. And in terms of replication, all the Amazon managed services actually keep the data in 3 data centers at availability zones. That option is configurable in Kafka. You can choose to keep 2 copies or less. And then in terms of throughput, there's no limit in the amount of throughput that these systems can handle. And we walked through parallel consumption. That's not possible in SQS, but then it's possible in other services. And we also walked through streaming map reduce, which is not possible in SQS or SNS. And then I've also given the record sizes in all these services. Last but not the least, cost. So when I compute the cost for persisting streaming data, Kinesis turns out to be the lowest cost service. And then if the same payload is persisted in DynamoDB streams, it's a little more expensive because I think you're paying for the table cost, which is there forever. And then if you are actually using SQS or SNS, then again the cost is slightly higher. And in the case of Kafka, the cost is fairly low, but at the same time, the admin cost is something that even needs to be factored in, even though you get EC2 instances, etc. for fairly inexpensively. The cost of administration in the case of Kafka is slightly higher. So this gives you a sort of how do you compare and contrast between these services. So, and going into the file storage, the single best advice I can give you as to where to put your file data is Amazon S3. Because it's natively supported by many big data frameworks such as Spark or Hive or Presto, and then one of the most interesting characteristics here is that it decouples storage from compute, unlike HDFS. If you're running an HDFS, if you're using HDFS, you need to have a cluster humming all the time for the data to be alive or available. But in the case of S3, you don't have to run a Hadoop cluster to have the data there. So literally, it's a storage service where multiple Hadoop clusters can process the data in parallel. Each can use its own instance types, either memory, depending upon what type of EC2 instances that you need. If it needs a lot of memory, you can pick the right instance type. If it needs a lot of CPU, you can pick the right instance class for members of your Hadoop cluster, if you will, to process the data in S3. Also, S3 is very highly available and is designed for 11.9's durability. There's very unlikely that you're going to lose any data in S3. And it's also multi-AZ. Data is replicated in multiple data centers. Whereas if you're running HDFS on EMR, it's a single data center solution. And the other piece there is also tiered storage. S3 has various storage classes. Standard, infrequent access, and Amazon Glacier. You can set a lifecycle policy and simply set the policy such that, after a specific timeline, let's say 6 months or a year or 2 years, automatically move data from standard to Glacier or standard to infrequent access can be a policy. It's a simple policy you do set, and then the S3 service actually does the move for you. And so I think it's also fairly low cost. About 3 cents per gigabyte per month is the S3 standard pricing, and then to a penny per gigabyte I think 7/10 of a penny per gigabyte per month in the case of Glacier. So, I think the one biggest recommendation that I can give you from big data processing is that all your big data files, big data should eventually go into S3, and you should ask yourself, why you can't do this with S3 if you try to actually put this elsewhere. And then what about HDFS and Glacier? Typically, with the availability of S3 and the durability of S3, HDFS is used for infrequent data access. Sort of think of that. I think of that as a hot data cache. Let's say if you're running a ETL pipeline, if you will, with multiple stages, the data, this first stage actually processes the data and hands off to the second stage. That's an area that you could consider using HDFS. We also, Amazon EMR also has an EMRFS, which adds consistency to S3, which can also solve that problem for you. But HDFS is frequently used as well as an intermediate temporary storage mechanism. And then on the other extreme, you have Glacier. So the way I look at this is, sort of a tiered storage with HDFS being used for very hot data access or intermediate data access and processing, S3 standard for all your big data, and then you basically set a policy to move the data to infrequent access or to Glacier. So now let's look at the database and search. And so this is an anti-pattern for building your big data database subsystem on AWS. Putting everything in a relational database system. Well, I use the Swiss Army knives because it's an interesting terminology. This is actually a Swiss Army knife. If you actually look for that on Amazon.com, it used to cost about $800. So the problem with the relational databases is even though they've been around for a long time, they do their function very well. It is fairly hard to scale a single dimension. For example, if you need a big screwdriver to fix something, then you need to get a big Swiss Army knife. For example, if you applying the same terminology to databases, let's assume if a workload does 100,000 writes per second and 10 reads per second. So if you were to do this in DynamoDB, you could simply ask for 100,000 reads, writes per second and 10 or 10,000 reads per second. But then in the case of a relational database, you're going to size this for the peak of the peaks. Therefore, the other pieces come along. So it's not a very efficient way of solving big data problems. So that's not the case. How should you think about your database and search tier? I think the best way to think about that would be to think of that as NoSQL and SQL and complementing this with caches and searches. There's a lot of NoSQL options on AWS, starting with Amazon DynamoDB, Cassandra, HBase, and MongoDB. And the same, you have all kinds of engines. If you're using a managed service such as Amazon Relational Database Service, you have the MySQL, PostgreSQL, Oracle, and SQL Server engines. And also you have Amazon Aurora, which can store up to 64 terabytes of data, and then can have 16 read replicas. So complementing the core NoSQL and SQL pieces with search and cache is fairly important. In the case of the cache, we have Amazon Elastic Cache, which has two engines, Redis and Memcached. And also we recently announced Amazon Elasticsearch Service for all your search analytics, if you will, as well as Amazon Cloud Search has been there for a while. And often the question that comes to me is, well, if you were to use this architecture, how do you keep all these things in sync? Here's a architecture for reference. I call this sort of materialized view architecture, where your data goes into a NoSQL system, such as if you put this in DynamoDB, you can actually have AWS Lambda or a Kinesis client library process the update streams. The update stream or DynamoDB streams is a mechanism where your changes into a table are persisted in a stream for 24 hours. You can have downstream applications and take these changes and apply it to other systems such as search or caching mechanisms. So what I've done here is basically you can write a little Lambda function that will simply process the DynamoDB streams and propagate the change to a search subsystem such as Amazon Cloud Search or Elasticsearch, or you can also push that out to Elastic Cache. So this way, from an application perspective, even though that there is an eventual consistency here of maybe about some tens of milliseconds, you'd be able to use the right tool. If you're dealing with search, using a search engine is the best thing to do because it can do millions of intersections per second, if you will, hundreds of thousands, I should say, of intersections per second. And just wanted to leave that as a thought there. Now, the other dimensions to consider when you're picking your data store is data structure, access patterns, your data access characteristics, and cost. We'll go into the specific scenarios here. If your access pattern is, for example, put or get, you should be using a cache or NoSQL. If it's a simple access pattern where you're dealing with one-to-many or many-to-many relationships, you should be using NoSQL. If you're dealing with a lot of cross-table joins or transactions, then obviously a SQL or relational database is the best thing to use. If you're dealing with faceting or search, a search engine is the best thing to use. Sounds pretty simple, but I think it's an important consideration when you're building scalable systems. And in terms of data structure, if you look at it from the data structure, if you're dealing with a fixed set-schema, then SQL or NoSQL is the best place to put your data. If you're dealing with a JSON, a schema-free data format, then most NoSQL systems support JSON as a first-class data type. So using a NoSQL or even a search would be the best place to put that data. And again, for a key value scenario, either caches or NoSQL is the best place to put your data. So the other thing, as a designer, another thing that I keep in my mind is thinking of your data as hot data, warm data, and cold data. Typically, hot data, you deal with smaller volume of data, very fast-moving data. Typically, you expect millisecond or sub-millisecond latencies, and your durability. Even though a database should be durable, you keep multiple copies of this. In general, the durability of very hot data stores is relatively lower unless there's multiple copies of this. The request rate tends to be very high, and then the dollar per gigabyte is high, but there's just one dimension. Again, as you move towards the right, you're dealing with bigger data sizes, smaller, larger item sizes, and you expect more latency, and durability tends to be very high, and the request rate tends to be lower, and the cost tends to be fairly inexpensive. So as a mental map, this is how I think of the various, big data database storage options. This is a mental map. This is by no means, fully accurate, but as a designer, this allows me to pick the right tool. But in some cases, you may end up with two tools. Then use the cost to break the tie in some cases, and then what I've done here is the structure on the left side is low to high. So for example, data in S3 is low structure. It's a key value, whereas in a SQL, it's well structured. It's a high, so it's a SQL is below S3. From left to right, the data is hot data to cold data. So for example, caches or NoSQL tend to have hot data, where the request rate is very high. The cost per gigabyte is higher compared to potentially S3 or Glacier. And then in the middle is SQL and search. So I want to leave this for thought, and I want to actually substantiate this further with some services. For example, in this case, what I've done is picked Amazon managed services such as Elastic Cache, DynamoDB, Aurora, etc., and then actually put them on a spectrum of hot, warm to cold. I've not given explicit numbers because they tend to slightly vary depending upon the workload, but in general, if you're dealing with caches, you're dealing with a millisecond or a sub-millisecond response times. If you're dealing with NoSQL or DynamoDB in this case, about 3 milliseconds is the response time. If you're dealing with a SQL engine, typically the response time is in milliseconds or second, depending upon the complexity of the query. Same thing for search. If you look at the request rates, towards the left side, the request rates in terms of requests per second tend to be very high. As you move towards the right side, your throughput tends to be higher, but the request rates tend to be lower. In terms of the cost, you're looking at probably two-digit dollars per gigabyte per month on the left side to probably 7/10 of a penny per gigabyte per month on the right side for Glacier. And similarly, I think the durability characteristics are low to moderate towards the left and very high towards the right. So as a designer, many of my customers found this extremely helpful. Whenever I present this, they take a snapshot of this. So I thought I would want to share this with you here. I want to substantiate further. I mentioned about cost-conscious design. One thing to note is here is a email that a developer at Amazon.com sent me. The person is building a subsystem that takes about 300 writes per second. The object size is about 2K, and the storage per month is 1.5 terabytes, and then the request is 777 million objects per month. What storage subsystem should the person use, S3 or DynamoDB? To break the tie, it'll be there's a tool called Amazon Simple Monthly Calculator. I find that extremely helpful. If you plug in the numbers into the Simple Monthly Calculator, it gives you a projected bill. In this case, it says, well, DynamoDB is going to cost $644 versus S3 is going to cost $3,932. For many customers, they sometimes, when I throw this as a quiz when I'm presenting, and people tend to pick S3, but the surprise there for them is, well, the put and the request rate, S3 is designed for large amounts of data. I think from a cost perspective, it's optimized for bigger objects, whereas in the case of Dynamo, it's optimized for smaller objects, at least from reference to cost. I mean, it's not that it won't work in S3, but then you're going to tend to pay slightly higher. So actually going through the cost exercise actually makes you pick the right tool. If there is actually an overlap, you could do it with both services in some cases. Just to contrast that, what I've done in this slide is actually increase the object size from 2K to 32K. As you will see, Dynamo in that case is going to cost, DynamoDB is going to cost $10,000 per month versus S3 is going to be around $4,588 per month. So S3 is the winner in the second case, and Dynamo tends to be the winner in the first case. So I mean, it's just, again, you could get by with both services here. I wanted to show this as how cost helps you to sort of pick the right solution for you at the right cost. Now let's look at the process and analyze. So we walked through the collect and the storage space, and then we went through how to pick the right tool there. Yeah, and then now let's look at analysis. So the analysis means different things to our process. It's interchangeably used, means different to different people. You may be going through an ETL processing. You may be thinking about building interactive dashboards. So interactive analytics is one class of analytic applications. Batch-oriented analytics or batch analytics is another class of applications. Again, when you're dealing with real-time analytics, such as fraud detection systems or alerting systems, I tend to call that real-time analytics subsystems. And then again, more recently, you have machine learning where you're doing either semantic analysis or predictions. So in the case of interactive analytics, you typically take a large amounts of warm data or cold data, and you want the result to come back in seconds, right? So if somebody is actually sitting in front of a dashboard, slicing and dicing, you don't want the person to go get a coffee. Rather, the answer should come back in a few seconds. Similarly, in the batch analytics subsystems, the normal expectation is the batch runs in minutes or hours or days in extreme cases, right? And then running a Hadoop cluster and running a Hive or a Pig, or more recently a Spark job to actually generate your daily or weekly or monthly bill is a classic example for this. In the case of real-time analytics, there are two scenarios here. Typically you're dealing with a lot of hot data that's just happening right now, and you want answers in milliseconds or seconds. Business real time in terms of change data capture and the data appearing in a data warehouse. Most businesses are happy with about anywhere in the realm of minutes, 5 minutes to 15 minutes of the data flowing through from end to end. But in the case of alerting systems, you want this to happen in milliseconds or seconds, and then also, in some cases, most companies have a key performance indicator for Amazon.com. One of the key performance indicators may be the number of orders flowing in per minute. So having a key how do you create a dashboard of all the orders coming in per second? So if there's any glitch there, you can actually investigate what's going on. So I think so that's sort of a near real time analytics there. So again, machine learning gives computers the ability to learn without being explicitly programmed. So for example, when you're dealing with a classification problem, you tend to ask the machine learning subsystem, does this transaction look like fraud? And then I'm going to ask more questions in that case. Or, if a new customer comes into a website, a retail website, given the characteristics of the customer that we know, is this going to be a high value customer or a low lifetime value customer? Based on that, you may present various different experiences. Or let's say if somebody is searching on a retail website for, let's say, shoes, you want the subsystem to classify. Wouldn't it be nice to have, all the, sports shoes or dress shoes or sandals being, faceted that way? So, if people are feeding a lot of data into your system, feeding pictures, how do you make the system pick or classify? So classification is a problem, or clustering is a problem that you can deal with many machine learning algorithms. So what tools, analysis tools and frameworks will you use for this? In the case of machine learning, Mahout has been used for a long time. More recently, Spark ML and Amazon Machine Learning are very popular. For interactive analytics, MPP or massively parallel processing systems such as Amazon Redshift, Presto, Impala are a great fit. Spark is a general purpose engine in memory or on disk, so it can be used for interactive analytics as well. For batch processing, typically it's Hive supplemented with Big, Spark, or some of the old systems are still in MapReduce. For stream processing, people tend to use Spark Streaming or KCL for sort of a micro batch semantics. And then for real time, AWS Lambda is very popular, coupled with KCL as well as Storm, Apache Storm. So one thing I want to actually go back here is that Amazon Elastic MapReduce, gives you the framework not only to run classic MapReduce, but also to run Hive, Pig, Spark, Impala, and Presto. So it's a nice way of running a managed interactive analytics application or a batch analytics application. And so I've left you with a slide here on what stream processing technology should you use, and I'm not going to go through the specific details of this here. The key point often people forget sometimes is the fault tolerance piece, which is, some of these systems, let's say Spark Streaming, if you're running Spark Streaming on top of Elastic MapReduce, that's a single AZ solution. So if you need multi-AZ availability, then you need to be in a position to launch another cluster if, let's say, a single availability zone goes down. For example, in the case of Apache Storm, that's configurable. In the case of Kinesis client library, you can run Kinesis client library across multiple AZs. So if you have an AZ failure, your processing will move forward. In the case of AWS Lambda, multi-AZ is automatically built in. And the one other characteristic that I want to highlight here is that Apache's Spark Streaming or Apache Storm or Kinesis client library or Lambda, really the query latency is fairly low. If you're using Hive or Pig, for example, through the connector to Kinesis, then your processing latency tends to be much higher. I tend to think of this as batch processing system. So I want to leave this for further, as something that you can refer to later. Similarly, what data processing technology should you use? On the left side, Amazon Redshift is a petabyte scale, fully managed data warehouse. It has very high SQL compatibility. It's fully managed, so it tends to be a great choice for many customer workloads. But other customers are using, for example, Presto. If you want to leave the data in S3 and run a Presto cluster on top of Elastic MapReduce to deal with running your monthly reports or weekly reports and other SQL style queries for interactive analytics, that tends to be a great solution these days as well. A lot of customers use Impala as well, especially if they're coming from a Cloudera background. And then Spark is getting more and more popular for doing both interactive analytics as well. Hive classically is used for batch processing. And again, I want to kind of leave that comparison for you for future reference as well. So what about ETL? AWS Data Pipeline is a fully managed services that performs cron-like ETL with a lot of dependencies, and you can create very complex pipelines using data pipeline. Let's say even if your data is in your enterprise or data center, you can actually have a data pipeline that takes the data and moves it on to S3 and then processes it using Elastic MapReduce, and then actually eventually moves the data onto S3. So you can build a very complex pipeline using AWS Data Pipeline. We also have amazing partners such as Tenuity or Informatica and others to build very scalable ETL pipelines. I've given the reference to the partner solutions there. They have a fantastic video and other material that'll help you make the right choice there for your workloads. Last but not the least, consume and visualize. And in consume and visualize, I want to typically I want to think from a user-centric perspective. You have business users that are consumers, and you have data scientists and developers, the second class of consumers, and the third class of consumers is the very bottom, really an application or API that you can build on top of your streaming data. For example, if you have a device manufacturer that's doing something like a sports watch or something that people run with, and you want to throw an API that shows given my user show me my last run or my last walk results, what was my pace, what was my route. If you were to build a subsystem like that, that's in the consume phase. In terms of for analysis and visualization, we launched Amazon QuickSight. That's something that we were in active beta at this point. And then coupled with Tableau or Looker or TIBCO or MicroStrategy is an amazing place to start. And if you're building an application yourself using one of the libraries such as Kibana or Float or D3, this is by no means an exhaustive list. I just wanted to throw some examples there. Similarly, the notebooks are getting very popular now. If you can launch Bootstrap a Zeppelin notebook on top of an Elastic MapReduce cluster, or you can have an IPython notebook on top of a cluster that you can actually launch on behalf of your data scientists. The data scientists can basically create notebooks and share the notebooks across with other data scientists or the enterprise, if you will. R Studio is very popular as an IDE, and then the applications, I will touch on the applications using the reference patterns. Now, putting it all together, here is a reference architecture. I want to leave this reference architecture as a reference for you. We went through the stack from left to right. Nothing more to say here. Now, let's look at some of the design patterns. So this sort of I'm going to summarize the talk as we move forward. So when you're thinking of building a big data pipeline or a data bus, think of multiple stages, and the stages should look like something like store, process, typically repeats itself. And, so if you decouple the systems in such a way, then you can actually have multiple processing applications, derive data. In this case, you could write a KCL application, Kinesis client-level application that processes the data in Kinesis and puts that in S3. And also you could have an AWS Lambda that actually takes the same data in Kinesis and applies that into DynamoDB for storing the metadata, for example. So decoupling gives you the power of parallel processing. And then also from a processing framework, you could have something like Hive. If you are able to construct a pipeline like this, you can have something like a processing engine such as Hive go after data in DynamoDB or go after an external table that's in S3 and give a composite view that comprises of a join between your data in DynamoDB and S3. So the decoupling gives you the power to composite views from multiple data sources and populate them in parallel. If you put this together on the top, you have the data stores such as Kinesis, DynamoDB, HDFS, and S3, going from hot to cold. And then I've also drawn a line in terms of the processing latency from low to high. So if you look at real-time systems, you may be using actually Spark streaming or Apache Storm or AWS Lambda or KCL to process data in a very hot store such as Kinesis or Kafka. Similarly, if you're dealing with interactive analytics, you may be running Amazon Redshift, copying the data from a table, DynamoDB table into Redshift, and then having a UI in front of Redshift, either through one of the tools, QuickSight or Tableau and others, slicing and dicing the data in Redshift. That's sort of a classic interactive analytics. You could do a similar thing with having the data in HDFS or S3, and then using Presto, for example, or Impala, for example. And similarly for batch processing, you can batch process using Hive from DynamoDB or HDFS or S3. So that sort of is a mental map of how I think about when I put these two things together in terms of the temperature of the data and the processing latency. So now let's look at a few classic examples. How do you build a real-time analytics pipeline using these principles? For example, in this case, producers produce the data can go into Kinesis or Kafka or DynamoDB streams. Then you can have one of the consumers, it could be AWS Lambda or KCL or Spark streaming processing this data, and you may actually, store the metadata, the process data, you can keep the application state in the case of Redis or DynamoDB and have a D3 or a graphic library, paint a pretty picture or a KPI, or you can actually have, when you detect an alert, let's say if a pressure or temperature gauge readings are very high, then you can actually trigger Amazon SNS to send notifications to downstream systems. In order to do predictive analytics, you can also do real-time predictions. You can also do real-time lookups. If let's say if this pressure gauge or a temperature gauge reads a specific temperature, you can consult Amazon machine learning to see whether this device is going to misbehave, and then you can also send an alert based on that. That's how you stitch machine learning into your real-time analytics pipeline. Again, this is a classic architecture for interactive and batch. Most of the data goes into S3, and then if you're building an interactive pipeline, then you can use Presto, for example, and have a consumer, run SQL against your data in S3. Similarly, data in S3 can be used if you're building a batch processing pipeline. You can use Hive or Spark or Pig by putting your data in S3. This is at the bottom, and then have the consumer consume the data. Run batch queries on top of your S3 data. And you can also do batch predictions or real-time predictions. So let's assume if you have a batch of records, you want to find out if all these records are either fraudulent or these are your high-value customers. You can hand off the batch to machine learning, and the machine learning service will actually tell you whether, what the scores of this, what the scores are for the batch, and then that can be used in your downstream, used by your downstream consumers. I talked about Lambda architecture. I want to substantiate that with a specific example of an architecture. Data, typically in the case of a Lambda architecture, goes into Amazon Kinesis, and then you have a batch processing layer. In this case, I've used a KCL S3 connector to take the data and load it into S3. That could be done by AWS Lambda as well. Or we also launched a service called Kinesis Firehose that automatically does that for you. So if you put the data in Kinesis Firehose instead of Kinesis, the top, and you can designate S3 or Redshift as a landing zone for that. And then the answers can be derived out of Redshift or any other, Presto or Spark application that you can run on Elastic MapReduce for your batch processing layer. Similarly, for speed processing, you could use AWS Lambda or Spark streaming or Storm to process data in Kinesis and then derive an answer. Typically what happens in this case is you have a serving layer that you put in between your downstream applications or API, and that accumulates the batch process results or the speed process results. And you use, the classic stack there is either use Elasticache or DynamoDB or RDS or Elasticsearch to surface the answers at the right speed. Again, as I mentioned before, you could also use machine learning in this pipeline to build predictions into your application. So that's sort of how an end-to-end application that uses Lambda principles looks like in reality. So to summarize, you should be building decoupled applications, and then your application should look like data going into storage and being processed and then that stored process repeats itself and derive answers. You should be using the right tool for the job. We walked through how to use latency, throughput, and access characteristics to pick the right tool. We went through an AWS Lambda architecture pattern, leveraging the batch speed and the serving layers, and then how do you keep an immutable up-and-only log in S3, as well as, I've shown you specific examples of how to use AWS managed services for building applications fairly rapidly. And then last but not least, you should be cost conscious. We walked through an example. With that, I want to thank you for your time, and I hope that was helpful. Hand this off to Jorge.
Thanks a lot, Siva. Many thanks to our audience for submitting all the great questions. And also to our moderators, Keith and Babu, for facilitating the questions. They've been very, very busy. You probably heard the keyboard tapping through the chat. And we'll also try to answer a few more questions right now, but I apologize in advance because we are almost running out of time. So we'll try to address some of the most popular questions as well as some of the questions that we didn't address on the chat. So the first question here, Siva, what technologies you would recommend for applications that require analysis of large data volumes with very low latency? For instance, analyzing stock trading, algorithms, or transactions.
Yeah, large volumes, when you think of large volumes, typically what happens is, again, it depends on whether you're doing, in this case, it looks like, putting data in S3 and running Spark on top of EMR could be one solution. The other solution is potentially putting your data in S3 and uploading it to MPP data warehouse, such as, Redshift, or if you prefer to use, Presto for running queries, that would be another way of doing this. Again, it depends upon, in this case, if your time to answer from the time the data is born to when you get the answer is longer, you have more options. But those would be classic examples of how people are dealing with this. So if feel free to, if I'm not addressing your question, feel free to actually rephrase or send the questions to us. I presume there's a way of reaching us as well.
Yeah, so we will be reviewing the questions, so we'll try to follow up on those that we didn't address completely. Second question, could you put a number as an example of what you will consider a hot data request when we talk about the hot data, warm data, etc.?
Yeah, I think it's, what I think of hot data is either requests for, one way of thinking about this is the request rate, tens of requests per second. The other way people think of hot data is really the number of requests per gigabytes of data, right? That's touching the specific, in terms of gigabytes of data. So in general, hot data stores tend to be fairly very high request rate, such as it feels like talking to a cache or talking to a NoSQL store where you're dealing with like millions of requests per second. In the advertising world, a hot data store typically could be DynamoDB serving, millions of requests per second, and then with a cache, supplementing with a cache that can also, serve hundreds of thousands of requests per second.
Thank you. The next question is, how much does it make sense to reach for raw data in S3 every time for EMR versus storing some process data in DynamoDB and then use it on EMR?
That's a great question. It really depends on the time to answer, right? In some cases, what happens is, for example, I was dealing with a scenario where it's an advertising. The customer was trying to build a system where, should I serve this ad to the specific device? The time that they had to make the decision is a few milliseconds. So therefore, actually, what ad did I serve to this device last? If that ad was kept, in order to serve the new ad, you're just simply doing a quick lookup for the specific device and a specific ad to figure out what, whether the ad needs to be served. That kind of a lookup can only happen, using a NoSQL, for example, like Dynamo, or it could be sort of a cache, elastic cache of some sort. So for that scenario, you need a DynamoDB to look up very fast. But if you are going to be running a process such as, even if you run the Spark in memory, still it's not going to be as fast as probably looking up doing a quick lookup in the case of DynamoDB. So if you have some time to process the result, and it sounds like sort of an analytics query, but in-memory analytics, potentially, Spark would be on top of EMR, would be a consideration there.
And this question actually comes very, very often, so I would like to address this one as well. It's kind of related. When using S3 versus HDFS, is I/O performance comparable when running, for example, a MapReduce job?
Yeah, I think the I/O performance it depends upon when you say I/O, as long as you have, from an S3 perspective, the I/O performance is comparable as long as HDFS tends to be faster than S3. But then again, that's why when I was, in the presentation, using HDFS as a very hot cache for processing purely, data between stages makes sense in many scenarios. But as a persistent data store, S3 makes a lot of sense. So is the I/O performance, certainly HDFS is faster than S3. But then again, if you're actually doing a large number of clients parallelly accessing the data, what really matters is how long is the time to complete the computation. So if you have a wide enough cluster that can parallelly, and your problem can be broken down across multiple nodes, that never really is a factor. So you can actually have, even though the latency in HDFS tends to be slightly faster, the throughput is slightly more, you're able to do the computation in an acceptable time. So before you consider HDFS for that, I would try to see if you can solve the problem with S3.
And I may add, we like one of the great advantages to using S3 is we have customers who have, for example, batch workloads that run at night, so they can spin up a cluster, do the processing, and then turn it back, and all the data is in S3, so they don't lose any data. We have like 1 minute, so maybe time for one question. I'll let you pick the last one, Siva.
Yeah, can you stream high loads into S3 and then consume the data out, or do you need DynamoDB for that? You can write to S3. For example, if you're writing to a specific bucket, I guess if your data set size is very small and your request rates is extremely high, millions of requests per second, or hundreds of thousands of requests per second, DynamoDB tends to be a good place to write that data. But if your data set if your data, files are large, megabytes, tens of megabytes, typically S3 tends to be a better place to copy the data. So, if you're talking throughput, S3 can give you the necessary throughput if the file sizes are large, right? But if the data is tiny or small, a few kilobytes, then DynamoDB would be the best place to actually, put the data. Again, if you put the data in DynamoDB, you can copy that over in there's a Hive handler for EMR. You can copy the data to S3 as well. And basically you capture the hot data in Dynamo and copy the data to S3, for downstream processing as well.
Okay, perfect. Well, that's all the time we have. It's 10 a.m. sharp here in the Pacific. So thank you so much, Siva. And
thank you, everyone. Really appreciate it.
Yeah, thanks a lot for your time. Thanks also to our QA moderators, and of course, thank you to all the audience. If you have any comments on this webinar or any previews or upcoming webinars, any suggestions on topics you wish AWS to address in the future, please feel free to send those via email at aws-webcasts@amazon.com. Your feedback will help us improve our webinar programming. Thanks again for taking the time to join us today, and have a great rest of your day.